In this video, we're going to discuss one consideration that can help guide the process, the bias-variance trade-off. Suppose that we wish to model 3 p.m. temperatures in Wollongong, Australia. How we go about building such a model is largely guided by our precise goal. For example, consider two common types of goals. First, suppose we merely wish to understand and make inferences about the association between 3 p.m. temperature and 9 a.m. temperature when controlling for month. This goal specifies the exact model or the exact set of predictors that we want to use. Mainly, we can build a model of y by the two predictors here. Consider a second type of looser goal. Suppose we wish to build a model that produces accurate predictions of 3 p.m. temperature using data on any variety of predictors. Could be 9 a.m. temperature, month, humidity, and so on. In this case, we don't care so much about what predictors we end up using, so long as they produce good predictions of 3 p.m. temperature. In embarking on such an open-ended scenario, we need to be mindful of the bias-variance trade-off. Consider a specific example. Suppose we wish to model 3 p.m. temperatures in Wollongong by the day of the year. As we should expect for a city in the southern hemisphere, the data reflect a quadratic relationship. Temperatures are high at the beginning of the year, low in the middle of the year, and then rise again toward the end of the year. To model this relationship, let's start really simple. Consider the model with no predictors. In this case, the model is a flat line defined by intercept beta 0. Clearly, this model oversimplifies things quite a bit. Whereas we observe a quadratic pattern in the data, our model assumes that temperatures remain flat throughout the year. This rigidity then fails to pick up on the general relationship between temperature and time of year. We can improve our model by adding some flexibility. Specifically, we can consider a quadratic model. In this case, we effectively have two predictors, x and x squared. And the results are pretty good. Unlike our previous model, this model does capture this general relationship between temperature and time of year. But we might ask ourselves if we can do even better. For example, perhaps we can add even more flexibility using a 12th order polynomial model. This model now has 12 predictors, x, x squared, on up to x to the 12th power. But it looks like this additional flexibility takes it a little too far. In looking at the curve here, do we really think that it provides a good picture of the relationship between temperature and time of year? No. It's way too flexible, hence wiggly. It's doing a good job of picking up local trends, like the trend up here in the top left corner. But the cost here is that it loses the bigger picture of the relationship between temperature and time of year. Stepping back, our three models of temperature are shown here. The first was too rigid, and at the other extreme, the third was too flexible. The second model provides a nice compromise. These comparisons reflect the bias-variance trade-off. Let's first consider the general concept. Suppose we are playing a game of darts. We get the most points if our darts land in the inner green circle, and the least points if they land in the outer red circle. The best players will consistently get their darts within the green circle in the center of the board. The fact that the darts, on average, land in the center of the board demonstrates that there's no bias in this player's outcomes. The low variance in the darts locations demonstrate that this player is consistent. But not all players are so good. For example, consider another player. This player might consistently throw low-scoring darts. Thus, they demonstrate low variance, but high bias. Their darts aren't landing in the center of the board. Between these two extremes are those players that consistently throw darts that are slightly off-center. Now, if we wanted to win the game of darts, which we do, it's better to be the player with no bias and low variance. Unfortunately, consistency or low variance can be difficult to achieve. That is, some players will have high variance in their dart throws. Now, if we had to pick among the 6 players here, we'd still prefer to be this first player, that with no bias and low variance. However, suppose that this perfection is out of reach, as it so often is. Instead, suppose we had to pick between being a player with no bias but high variance, or low bias and low variance. Which would you pick? The winner is the player with low bias and low variance. That is, it's better to consistently take on a little bias than to have no bias but high variability. This scenario reflects the bias-variance trade-off. Let's connect this back to regression modeling. Reconsider our 3 models. Again, we saw that the first was too rigid and the third was too flexible. Our first concern is the bias in each of these models. The question here turns from how far off the center of the board does a dart tend to be, to how far do the observed y values tend to fall from the model. In general, the more rigid the model, the greater the bias. Specifically, notice that the observed y values tend to fall much further from this 0 predictor model than they do from the 12 predictor model. They're much closer to the curve. Thus, if considering bias alone, we might pick this 12 predictor model, or we would pick this 12 predictor model. But we don't consider bias alone. We also consider variance. The question here turns from how consistent is a player from dart to dart to how much might the model change if we used new data. That is, how stable is the model? So let's try it. Let's rebuild our 3 models using a new sample of 40 days. Perhaps not surprisingly, this 12 predictor model was overfit to our original sample data. Thus, it changed quite a bit when we used new data. Thus, this model is the least stable or the most variable from sample to sample. It's simply not very reliable. On the opposite end, notice that the 0 predictor model changed very little from sample to sample. Thus, it's the most stable or the least variable from sample to sample. This makes sense. By ignoring time of year, this model only takes into account the average temperature. This average temperature, slightly below 20 degrees, doesn't change very much from sample to sample. Putting this all together, we've observed the bias-variance trade-off. As we make our models more flexible, they become less biased, which is good, but more variable, which is bad. That is, bias and variance are inversely related. For example, that the flexible 12 predictor model enjoys low bias, it suffers from high variance or instability. Just as with darts, the high variability here is enough to make this model a bad player, so to speak. At the other end, the rigid 0 predictor model enjoys low variance, but it suffers from high bias. In other words, it's just consistently bad. The 2 predictor model wins the bias-variance trade-off. It takes on a little bias in order to decrease variance. As such, it increases the overall prediction accuracy while preventing overfitting. In conclusion, the observations we made about our polynomial models apply in general. Overly simple models with few or no predictors tend to have higher bias, but lower variability, that is, high stability. Overly complicated models with lots of predictors tend to have low bias, but high variability, hence low stability.